Hey, so today with us is Robert Bedington
Hi.
from SpeQtral,
Yes.
being based in Singapore. And we continue our conversation with really bright companies and individuals working on amazing projects. And today we're here in Logan, Utah. We wanted to have a chat with Robert. He's doing this amazing project at his company. And yeah, let's hand it over to Robert. Tell us about, first yourself and your background, and then let's discuss what you guys are doing.
Sure. So my background, originally I was a physicist. I worked in space plasma instrumentation for my PhD, making miniaturized instruments. From there I moved to JAXA and was working on miniaturized plasma instruments at JAXA. And then nearly 5 years ago now I moved to Singapore and started working with a group at the Centre for Quantum Technologies at the National University of Singapore, where they're making miniaturized entangled photon sources for CubeSats.
Okay, can you explain what is that?
Yes, that is not straightforward. So an entangled photon pair source makes pairs of photons, so particles of light, that are correlated in ways that classical physics cannot explain. So these pairs of photons have a spooky connection between them. This is how Einstein described it.
That's how you named the first satellite, right?
So yeah, our first satellite is Spooky 1, and this is Einstein scared of the entangled ghosts here.
We like it.
Yeah, and so this entangled photons, this property has various uses in technology, and the most immediate use is in the generation of encryption keys, very, very secure encryption keys that can be shared between two remote parties with tests that can be made that can verify that there's no eavesdropper listening into the
proper
distribution of the
R&D.
key.
It's not proper like pure science. It actually has the commercial application of it, right?
I mean, it's both.
Yeah.
So there's a big kind of scientific aspect to this, but there is also an immediate technological commercial use case, and that's what we're exploiting at SpeQtral.
So basically, you use that quantum effect of quantum entangled and try to apply it to the modern cryptography, right? Is that what it is?
Yes, I mean, so it's actually not so modern in that the quantum key distribution, this technology for generating encryption keys, was developed in the 80s, and then the entangled version in the early 90s. It's just only recently that it's become practical to implement this on a commercial scale, and also only recently that there's been a real kind of push to adopt these technologies. And that push also comes from quantum physics, and that this is quantum computers, because quantum computers have received a lot of funding, a lot of research recently, and they're really, like, some people charting the performance of quantum computers are saying this is moving faster than Moore's law, and the reason this is driving QKD sales is because quantum computers, we know, will be able to crack conventional encryption methods once they get powerful enough. So the algorithms required to break public key encryption schemes, particularly RSA, which is the most commonly used encryption method, the methods to break this have already been worked out. The quantum algorithms that you'd need to run on your quantum computer, they were worked out in the 90s. And so we're just now waiting for the machines to get powerful enough to run these applications, and then there's a real kind of security problem.
Right.
Whereas QKD, we can prove.
How do you spell out the QKD?
Sorry?
How do you spell out the QKD? What is it?
Oh, so quantum key distribution.
Okay,
So quantum key distribution is this method of making encryption keys using photons rather than using mathematical tricks. So public-private key encryption is incredibly convenient, but it's based on mathematical algorithms. It's based on the assumption that the mathematical problem you use to encrypt your message is too difficult for a conventional computer to unpick. Yeah.
Right.
And that's basically true for modern computers. But we know that won't be true for the quantum computers of the future.
So basically, you're developing a solution
Yeah.
for the future world where the quantum computing is that spread out that people can actually use that to crack the codes of the traditional, let's say, encryption keys, right?
Yeah, that's one use case, or that has certainly been driving investment and improvements in QKD. But there's other reasons why you would want to use QKD. I mean, it is provably the most secure method for producing encryption keys. So for the people with the biggest secrets and the deepest pockets, this will always be the most attractive way for them to make encryption keys, regardless of the progress of quantum computers.
Okay, here's a tough one. Why satellites? Why to put this technology on satellites?
Why satellites? Because we're talking here about sharing individual photons, so that the key is encrypted in individual photons, well, streams of individual photons. We have to identify each photon one by one to make a key from this. So we can't amplify these signals. So the key is encoded in quantum states on these individual photons, and quantum physics just does not allow you to make copies of this. That breaks the whole principle. So this means that you're very sensitive to losses. You can't afford to lose these photons. You have to transmit them. So this means that if you're sending them over optical fibers, which is the normal way you would communicate optically, there's a distance limitation. There's a distance limitation of 50 to 100
and the risk to lose the photons otherwise.
And if you go much longer than that, then you're simply not going to get any kind of usable number of photons coming out the other end. They'll all be absorbed by the glass in the fiber. And the situation is slightly better if you go through free space. So if you just go through the air, you can do so well. If you go through vacuum, even better. So communicating between a satellite and a ground station on the Earth, you have a bit of atmosphere in the bottom, then a bunch of vacuum, and then you're able to kind of close the link and to successfully detect some photons if you send them from the satellite down to the ground station, or possibly vice versa.
That makes sense. So you distribute the keys for the photons from a satellite.
Yes. So the trick here is that you have to use your satellite as a trusted key exchanging node. And if you can trust that satellite as a key exchanging node, then you can use this as a way to distribute encryption keys around the globe.
Got it. And how far along are you? Because this seems like a very tricky and expensive venture to start with. So how far along are you?
So we have, SpeQtral is a spin-out company from National University of Singapore. And as the university, there's over a decade of research that's gone into this. So developing the ground-based free space links, and more recently the satellites. So we have a couple of satellites in orbit right now. The latest one, Spooky 1, was put on orbit in June, and that's demonstrating the latest version of our entangled photon source. So that's just demonstrating that the source survives inside the satellite, and this technology is kind of space-proof, so kind of raising the TRL of that technology. The next version of that, which is still a university project, is being prepared for the QKD CubeSat mission, which is a follow-on mission. It's a UK-Singapore intergovernmental mission that will demonstrate the full space-to-ground QKD using a CubeSat platform. So that will launch in 2022 or so. And then
that will further increase the TRL of the whole.
So that will be a demonstration of the full system, and then the technology developed by NUS side of that will be licensed by SpeQtral for commercial purposes.
And who will be your clients for that solution once it gets ready?
So QKD CubeSat's an academic project, but the versions which SpeQtral sell, they will be for anyone that wants to buy it. But these are like telecoms operators and banks and financial institutions are kind of target customers.
So anyone who relies now on the RSA cryptography
Yes,
and
or
feel the threat from the quantum computers might
Yeah.
be able to use that.
so governments, military, anyone who has secrets they want to keep safe,
Right.
should be looking into this,
Yeah.
and many of them are.
How difficult is it going to be integrate that into existing platforms that you guys have? Like, what would they need to do in order to implement this technology down the road?
So it depends. I mean, there's many different configurations for secure networks, but this QKD is really applicable where you're using symmetric encryption already. So if you're using AES encryption to secure data channels, then QKD can be used to supply the seed keys for those AES links. And these seed keys would normally be supplied either over the internet using public-private key encryption, which we've discussed as potential future issues, or they might currently be provided by couriers. So people with briefcases or USB sticks, literally going to each site, plugging these in,
physically distributing the keys themselves.
Exactly. So QKD provides, or satellite QKD provides, a more automated, arguably more secure, because you only have to trust the satellite, that the link is inherently secured through quantum physics. And so it gives you the opportunity to refresh your keys more frequently. So if before you were only doing it once every 6 months or so, or once a month, this time you could refresh your keys with every successful flyover of the satellite on the ground station.
Every connection of a ground station with satellite, basically.
So we were just talking about refreshing the seed keys off your AES module.
Got it. I
mean, there's other ways of applying this. So you can use this for it's called one-time pad encryption. So that's where the size of the message is the same as the size of the key. So this is the most secure way you can transmit a message.
The messages themselves.
But that's just very challenging, because you need, you can either a lot of key or very short messages for that to be successful.
Here's the last one. When do you think the quantum computing will potentially be that spread out that it will start to pose a threat to compromise the existing security networks? How far we are from that future?
This is anyone's guess, really. So there's multiple aspects to this. So the goalposts are kind of moving as well. So there's quantum computers are improving at faster rates than we were expected, if the reports are to be believed. But also the computing power required to break the current encryption, that's also going down, because people are finding improvements to the algorithms, and whereas before they might need millions of qubits, maybe that's kind of halved as they as the new algorithms.
Okay, let me rephrase that. Will we be on time with your solution before this threat?
Well, okay, and so there's another aspect to this, and that's how long do you need your data to be secure? So if you need your data to be secure for 50 years, 100 years, then maybe it's already too late. Because if someone has intercepted that data as it travels along a data channel, and they've got a copy of that which they've stored, and they've got a copy of your public key because that's public, then they just need to sit and wait, and they can decrypt that later when that quantum computer comes along. And 50 to 100 years, we're for sure going to have a quantum computer. So for those guys with a 50-year plus requirement on their data security, I'm sorry, it's probably too late. So then it comes down to, well, maybe it's a 10-year the lifetime of your data. Well, then you need to think about, well, what's the probability of a quantum computer appearing in that time, and what is your risk appetite there? So maybe there's a 1% chance of a quantum computer that's powerful enough coming on in 5 years, or maybe there's a 1% chance that it already exists and no one's talking about it because it's hidden in some military.
You probably can get an insurance coverage in that.
But you have to consider, is 1% manageable, or is that already too high?
Got it.
But yeah, honestly, we don't know.
Yeah.
Quantum computers going to come along.
Well, great, Robert. Thanks for giving us a glimpse of the world of quantum computing and quantum key distribution. It's really exciting, and yeah, good luck with all your projects, and
you.
wish you all the best.
Thanks a lot.
Great, thanks.